Hello. So, in this example, we're going to be doing an example of an implicit differentiation. So, remember, the whole thing with implicit differentiation is it's really just the chain rule, and recognizing that if we have basically a letter that doesn't match the type of derivative we're taking, that means that we sort of have to leave that part as some unknown differential. Okay, so let's see what we mean here. So we're given this equation up here, right? So we're told, okay, we have some xy squared, and that equals, let's see, 13 square root of x plus 1, okay? And we want to take the derivative of this. So when we take the derivative, we're basically going to treat x and y as the same sort of deal, even though y is different. But sort of a key thing to remember is that when we take the derivative, we want to sort of pay attention to what it's with respect to. So like the unseen step, I guess, would be the following. Would be that we're sort of declaring we're going to take a derivative with respect to x of both sides, right? So xy squared. So normally we don't have to write this step. I just want to sort of show how to remember, how to know when we want to use implicit differentiation versus when we don't have to worry about it. Yeah, oh well. Let's see, so that's square root of x plus 1. And yeah, it's going to bug me, so I'm going to go ahead and erase that and change the color because, there are things you choose to care about, and that's just one of them. All right, so the idea here, though, is that even though we wouldn't normally necessarily write this step, I can notice, right, that I have my dx, which is saying I'm doing it with respect to x. So whenever I run into a letter like y that isn't x, then that's when I use the implicit differentiation, okay? So otherwise, I sort of treat y as some other function of x, which is even, what it tells us, right? Y is a dependent variable dependent on x. That means y is some function of x. So when I look at this then, this would be sort of like looking at something like x times e to the x or something like that, right? Where it's some other function of x. In particular, that means I need to use a product rule, right? Because I have the two different things, so I need to use the product to sort of do the product of the two functions in order to get the derivative. So in particular, I want to do this derivative with respect to x of x times the second thing, just y squared, plus the first thing, x, times the derivative of the second thing. And it can be helpful to write this part out because, again, it's going to annoy me, so I'm going to change the color. So it can be helpful to write this step out because this will show why one of these things is going to have a y prime and one of them won't. So that is then, and then this is all just x, so I can actually just take the derivative of this straight up. So remember the square root of x, we really want to think of this, bust out yet another color here, we really want to think of this thing as x to the 1/2. That way when we take the derivative, we can do the 1/2 in front, subtract 1 from the power kind of deal. So the 13 is a constant, it just sort of hangs out there. I'm going to pull the 1/2 down and then subtract 1 from the power. So I'm going to get 1/2 minus 1 plus 1, okay? So I'll clean that up in a second. But this side I could sort of just cleanly take the derivative because there was nothing there's no y in this side, there was no product of functions or anything. It was just sort of a nice kind of side all on its own. This side, there's a little more work left to do. So derivative of x is just 1. So I don't have to write that, but I'm doing it just to show that I did actually take that derivative. Here I have x, and now I have the derivative of y squared. So this I could treat as, a function squared, so I'd bring down the 2 times the base y times 2 to the minus 1. But then I have the chain rule, which says, okay, y is some unknown function like f. So if I were doing f squared, I'd bring the 2 down, subtract 1 from the power, but then I'd still have to multiply by the derivative of that inner function, in this case, just y. Okay. And again, over here, I can sort of clean this up a bit. So this is 13 halves, just multiplying those two together. And 1/2 minus 1, so that's going to be x to the negative 1/2 plus 1. Okay. So last but not least, I can clean this up. So I'm going to get y squared. So then I have 2, so plus 2 times x times y to the 1, so just y. But then I have this derivative of y with respect to x, which I can write as y prime. But often it's sort of nicer to keep it in that sort of fractional differential form, so you can keep track of what's happening. So in particular, I could say times dy dx, but I will make a note underneath. I could also write this as y prime. Either of those is fine. They're both sort of equally common. I find this sort of a little bit nicer because it sort of keeps track of what happened, that I took a derivative of y with respect to x, whereas this is just saying I took a derivative of y somehow and doesn't really tell me with respect to what. But either one's fine. Equals 13 over 2, x to the minus 1/2 plus 1. Okay. So now I have done my derivative, right? But even though my initial sort of function was defined implicitly, I would like to, if possible, and it pretty much always is, at least at this level, I would like to isolate y prime, right? So I want to be able to get y prime by itself. So to do that, I'm going to move everything that isn't y prime or dy dx off to this side. So I have this stuff already, and now I'm going to move this stuff over as well. So on the left, I still have 2xy times dy dx equals, so then I have on this side 13 over 2 x to the minus 1/2 plus 1, that's all of this stuff. But then I'm going to have this thing come over, right? So I subtracted the y squared. And finally, my goal is to get this by itself, the dy dx, so I'm going to divide by the 2xy, right? So divide both sides by 2xy. And that's going to get me dy dx equals, and then this, I'm basically just going to leave it as it is. So I'm going to have 13 halves x to the minus 1/2 plus 1 minus y squared all over 2xy. Okay? So this is my final answer. So again, even though my original function, right, was given as this implicitly defined thing, I could solve explicitly for dy dx, and that was good, right? So that's what I wanted to do. Okay? So that's that. Hello. So in this problem, we are doing an implicit differentiation, right? So we're given a function, but it's implicitly defined, right? It has y's and x's all sort of mixed together. So we want to take the derivative of this with respect to x, but we have to account for the fact that, right, y is some dependent variable dependent on x, so we have to treat that with implicit differentiation. So start by writing out my problem, right? So I have y minus square root of y equals, let's see, 8x squared plus natural log of y. And in particular, right, I want that I'm taking the derivative of this with respect to x. So in particular, I'm taking the derivative with respect to x of both sides. So I'm just sort of squeeze it in here. And again, you don't necessarily have to write the derivative part, but again, it helps to sort of keep track of sort of when you need implicit and when you don't, right? Because the whole deal is whether or not they match. If the x and the letter, in this case y, don't match, then you need it. If they do match, then you don't, okay? So here, derivative with respect to x of y. So first I treat it like it were an x, meaning if I did derivative with respect to x of x, I would get 1. But because they aren't the same, then I have to multiply by the sort of inside, which here the derivative of y with respect to x, which gets me just dy dx. So it's a little redundant because really what I would be writing here is I took the derivative of y to get 1 times the derivative of y with respect to x, which is the same thing, but like that's the point, is I'm trying to show that like worst case you write 1 times right d dx of y, which is still the same thing. It wouldn't be wrong, you just don't want to go through an infinite loop. Regardless, derivative with y right gets me y prime or dy dx. Then same deal here, so I'm going to treat this sort of as a note here. Always good to treat your roots as powers. So this is really, I would think of this as x to the 1/2 power, right? So when I take the derivative then, I again treat it like an x, so I pull the 1/2 down. Y to the 1/2 minus 1. But because they don't match, then I need to multiply by the derivative of the inside, which again is dy dx, right? The derivative of y, because the inside is just y. So I get dy dx. That equals. So here, this is just, you know, a nice normal piece here, right, x. So I take the derivative of 8x squared. So that's going to get me 8 times 2, right, bring down the 2, x to the 2 minus 1. And there's no, right, because they match, I don't need to multiply by like dy dx or anything. And natural log. So again, if you haven't seen natural log at this point, which you may or may not have, just know that this is sort of video as a review as well as a lesson. So I'm going to assume that you've seen it, but if you haven't, don't worry about sort of needing to know it at this point. So you can come back and watch this part of the video later if you want. Anyway, so I treat this as an x. So in particular, if it were natural log of x, I'd get 1 over the thing. So it's 1 over y. But then, because it's not an x, I have to multiply by the derivative of the inside, which again, since it's just y, gets me dy dx. Okay? All right. So I've taken my derivative. My derivative step is done. But again, so even though my original one was defined implicitly, there's a good chance I can actually isolate my dy dx. So that's what I want to actually do here, right? So I'm going to get all the dy dx stuff on one side, and then all the non-dy dx stuff on the other side. In particular, both of these have a dy dx, as does that. So I'm going to move this over, and then this will be the only thing left on the right. Okay? So I'm going to have 1 times dy dx and then minus 1/2 y to the negative 1/2, right? So that's the 1/2 minus 1 times dy dx. And then this is going to get moved over, so I'm going to have a minus 1 over y times dy dx. All of that equals the thing that's still on the right here, which is 16x to the 1, right? So the 2 minus 1, okay? So all I've basically done is move this piece over. But now I have a dy dx on all of these terms, so I'm going to factor that out. So I have a dy dx times, so I still have a 1 there, minus 1/2 y to the negative 1/2 minus 1 over y equals 16x. And finally, my goal is to get dy dx by itself, so I'm going to divide everything by this. So I'm going to end up with dy dx all alone on the left, which is what I want. And on this side, I'm going to have the 16x, but then I'm dividing by this whole thing. So I'm going to get 1 minus 1/2 y to the negative 1/2 minus 1 over y. Okay? So again, in order to actually sort of start the process, right, I took the derivative, but I took it with respect to x. So that means everywhere where there wasn't an x, I ended up with a dy dx. And everywhere there was just x, I just did it sort of as normal. But then I wanted to isolate dy dx, so I moved all the dy dx stuff to one side, everything that wasn't to the other side, factored out my dy dx so that I had dy dx times a bunch of stuff, but then divide by that in order to get it by itself. So then that is my answer. Okay, so that is that.